Zeal Education Society, redefining excellence.
Hello, good morning to everyone. Myself Dr. Mahadev Unde, Professor in Electrical Engineering Department, Zeal College of Engineering and Research, Pune. In my previous video lecture, we have learned the BLDC motor. It is a special purpose motor used in e-bikes and so many other applications in feedback control systems. Now in today's video lecture, we are going to learn one more special purpose motor, that is the stepper motors. Let us have what are the general information, general things about the stepper motors, and later on we are going to learn the variable reluctance motor and the permanent magnet stepper motor separately. Now why the name stepper motor? Let us have a look on this. Now it rotates in angular steps and hence the name stepper motor. That is, the shaft rotates at a discrete angular intervals or steps in response to command signal received to its stator coil. Now for such a stepper motor, the torque available is from 1 micronewton meter for a wristwatch of teeny stepper 3 mm diameter to 40 newton meter up to a diameter of 15 centimeter. And the output power ranges from 1 watt to the 2500 watt. Now what are the types of stepper motors? Variable reluctance stepper motor and permanent magnet stepper motor. Now what is the step angle? The angle through which the shaft rotates by every command received to the stator coil. And it is given by beta equal to ns minus n nr divided by ns into nr into 360, or beta equal to 360 divided by m into nr, where ns equal to number of stator poles or teeth, nr equal to number of rotor poles or teeth, and m is the number of phases of the stator winding. Now for example, the stator poles are 8 number and the rotor poles are 6 number. Find the step angle. Now beta equal to ns minus nr into 360 divided by ns into nr, and that is equal to 15 degree. Obviously the same answer can be obtained, say m equal to 3. M equal to 3. Now for this, let us have another example. M equal to 3, number of phases equal to 3, nr equal to 4. And therefore beta equal to 360 degree divided by m into nr. So beta equal to 30 degree electrical. Now what is the resolution? Now the resolution is nothing but number of steps required for a one revolution of the shaft. Higher the number of steps, better is the revolution, and greater will be the accuracy of the positioning. These stepper motors are used in the robotics or the position control in a process control, or in feedback control also. But normally stepper motors are generally not used for the feedback control because it works in the steps. So the resolution equal to number of steps required for one revolution. So number of steps divided by per revolutions, and therefore resolution equal to 360 degree divided by beta. So, and n equal to, n is the shaft speed is given by beta into f divided by 360, where f is the stepping frequency in pulse per second, that is PPS, pulse per second stepping frequency. Okay. So for example, a stepper motor has a step angle 2.5 degrees. So beta is given to you, determine resolution. Number of steps required for shaft to make 25 revolutions. Then shaft speed if the stepping frequency is 3600 pps, pulse per second. Now see the solution. Resolution is nothing but 360 degree divided by beta. So beta is given to you, and it is found that the resolution is 144 steps per revolution. Now how many steps required for 24 revolution? For one revolution, 144 steps, and therefore for 25 revolutions, 25 into 144 steps, that is 3600 steps. Now the shaft speed n equal to beta into f divided by 360. Beta is 2.5, which is already given. Now PPS, frequencies pulse per second, that is already given, 3600 pulse per second divided by 360, and therefore shaft speed is 25 rps, revolution per second. Now see the variable reluctance taper motor. Why it is called as a variable reluctance? It is called variable reluctance because while making the steps, whether it is in forward direction or in a backward directions, the reluctance of the magnetic circuit formed by the stator teeth and rotor teeth is minimum, and it varies with the angular position. Means the reluctance varies as per the angular position, and that's why it is known as variable reluctance taper motor. Okay. Now see the construction. The stator has salient wound poles. Poles means nothing but the teeth. Poles means actually the number of teeth. The stator is made up of stacks of steel laminations. Means steel laminations are used, and it may be a single stack or multi-stacks. Later on we will see what is the multi-stack in the next video lectures. And rotor poles, that is teeth, are made up of ferromagnetic materials. It is a good quality of magnetic materials, and it may be, the rotor may be either solid or made up of laminations. Okay. Now see the principle of operations. The stator have 6 equally spaced salient poles. Poles means teeth, each wound with exciting coils, and rotor have 4 projected means salient poles of same width as that of the stator poles. The stator has 3 phases A, B, C, and has 2 coils. The 2 coils of the stators are connected in series with diametrically opposite poles, and they are sequentially excited by the driver circuit provided by DC pulses. The simple circuit is also shown there, and the truth table is also available. Now pay attention here. It is called variable reluctance taper motor because the reluctance of the magnetic circuit formed by the rotor teeth and stator teeth varies with angular position of the rotor. Now if you look at the first figure, pay attention here. Pay attention, this one. The outer is the stator, and it is made up of steel laminations. It may be either single stack or multi-stack. Here it is a single stack. It has 6 projecting poles, 1, 2, 3, 4, 6, and on which exciting coils are wound. Now the 2 diametrically opposite poles or 2 diametrically opposite coils are connected in series and excited by a DC source or driver circuit or electronically drive switch, or it is a sequentially switching. And when the DC supply is fed to this series connected coil, it produces north pole and south poles. Means in such a fashion that it produces north pole and south pole. Now it has 4 projecting poles on the rotors. It is made up of ferromagnetic materials, and it may be either solid or is made up of laminations. Okay. Now pay attention on the driver circuit or a simple circuit. Now here A and A dash, they are connected in series which are diametrically opposite. Okay, and say switch S1 is connected. Then the B and B dash, 3 and 6 are connected in series. So B, B dash, and to which switch S2 is connected. And C, C dash, that is the pole number 2 and pole number 5. These coils are connected in series, which is shown here, C, C dash, and switch S3 is connected. And to all these It is supplied by DC source. Its truth table is shown here, the ABC. Its direction of rotation depends on sequence of operation, sequence of operation of this switches S1, S2, S3 or A, B, C, A, and not on the polarity of the current flowing through these three phases. So there are three windings produce A dash, B dash, C dash, and which are supplied by the DC source. The three switches are connected there and they are operated sequentially, one at a time. Okay. Now let us have the operation. Now for this construction, stator poles 6 and rotor poles 4. So NS is 6, NR is 3, and how many phases are there? 3 phases, 3 coils. Okay. So 3 phases. So beta equal to NS minus NR into 360 divided by NS into NR, that is equal to 30 degree, or beta equal to 360 divided by M into NR. So it is also 30 degree. So you will get the steps of 30 degree. Okay. So at the beginning, say the coil S1 is closed and the other two are open. So the DC current will fade to the coils A and A dash, and the rotor poles 1 and 3 are aligned with the stator poles 1 and 4. So it has a minimum reluctance here. The reluctance equal to L divided by mu0 mu r upon A. Means the reluctance is minimum where the air gap is minimum. Reluctance is directly proportional to length of air gap. So reluctance becomes minimum when the stator poles and rotor poles coincides with each other. At this position, the reluctance between the rotor poles 1 and 3 and stator poles 1 and 4 becomes minimum, and there is no steps, the angle theta is equal to 0. Okay, I hope you understood it. Now switch on the switch S2, that means excite the coil B dash and keep the open S1 and S3. Say this one. When B and B dash is B dash, which is here, B dash is excited, it will produce the north pole and south poles. And this is a ferromagnetic material. Obviously, opposite pole will be produced here and it will get attracted. So what will happen? It will rotate, and the rotor poles or teeth 2 and 4 will align with 3 and 6 of the stator poles. See, observe this one. The rotor teeth 2 and 4 will align with stator teeth 3 and 6, and as compared to the reference position, the rotor teeth 1 makes an angle 30 degree. In other words, we can say the shaft rotates through a step angle 30 degree. Okay. Now let us switch on the switch S3, keeping S1 and S2 open. That is, the coil C1 and C dash is excited. Now look at this. Coil C and C dash is excited. If the coil C and C dash is excited, what will happen? Nearest to this 2 and 5 of the stator poles which get excited and produces the north pole and south pole along it, what will happen? This teeth number 1 will attract towards the 2, and the rotor teeth 1 and 3 will get aligned with stator teeth 2 and 5, which is shown here. See, the rotor teeth 1 and 3 will get aligned with stator teeth 2 and 5, and rotor, see, as compared to the reference, the teeth number 1, that is rotor, have another step of 30 degree, which has a total rotation of 60 degree. with reference position. So we got the two steps, 30 degree up to this. Now switch on the once again the switch 1, S1, keeping S2 and S3 open. When S1 is switched on, that is this one, A1 and A dash and A and A dash get excited. A and A dash get excited and it produces the north pole and south pole. Obviously, what will happen to this rotor pole 2 and 4? These two will get rotated in a forward direction through a 30 degree, and with the rotor teeth 2 and 4 will get aligned with stator poles 4 and 1, see, which is shown in figure D. The rotor teeth 2 and 4 will get aligned with stator poles or stator teeth 4 and 1 respectively, and rotor further rotate through a step of 30 degree in a forward direction, totaling it rotates through a 90 degree up to this. So in this way, sequentially, see here, when it is C dash is, means S3 is closed, we will get 60 degree. Now A dash is switched, means A is switched, it gets 90 degree. So in this way, sequentially, if you switch on A, B, C, A, the rotor will rotate in a forward direction, and if you switch in a C, B, A, C in the direction, the rotor will rotate through in a backward direction. Okay. Now let us see the direction of rotation. If the sequence of excitation of the stator winding is, say, A, B, C, A, the motor rotates in a clockwise direction, and if the sequence is A, B, C, A, B, A, C, sorry, C, B, see here, like this, C, B, A, again, C. So, C, B, A, C, it rotates in a counterclockwise direction. So the direction of rotation can be reversed by changing the sequence of operation. And not depends on polarity of the stator exciting current. Okay. Now here we are whatever operation we have made, that is that odds. Just a minute, I will show it here once again. The truth table. In the truth table, we have observed the steps position is 0, 30 degree, 60 degree, 90 degree. We got in these steps. But this is two large steps, and this is known as one phase on mode A, B, C, A. Now say, in order to get the better resolution, we have to obtain the small steps, that is half stepping, or it can also be obtained micro stepping. Now how to obtain this half stepping? Let us excite the winding A and B simultaneously. Now when the winding A and B are excited simultaneously, the current flowing through them will be equal, and they will exert the torque in a such a way that the rotor will become standstill midway between the full steps. See, in a previous, on a one step, it was 0, 30 degree. Now here, if you excite the A and B simultaneously, rotor will stop midway between 0 and 30, that is the 15 degree. Now excite the B and C simultaneously, the rotor will step ahead of 30 degree, but in between 30 degree and 60 degree, that is 45 degree. So in this way, let us have the truth table, say the two phase on mode, that is excite the AB together, A and B together, and keeping C open, the rotor will stop midway between the 0 and 30 degree. Then excite the BC simultaneously. The rotor will stop, or it will rotate in a forward direction through a step of 30 degree, but it will stand still position, it will stop in between the 30 degree and 60 degree, that is 45 degree. So if we excite further C and A together, next angle will be 75 degree. And if you once again excite A and B together, the next step will be 105 degree. Now if you operate half stepping, that is alternate single step, single phase on, alternate single phase on mode and two phase on mode, that is A, AB, B, BC, C, CA, again A and again AB. See, for A, if you excite A only, that is single phase on mode, only the supply is fed to the A winding, there is a zero angle. Then if you switch on A and B together, the rotor will shift or rotor will steps in a 15 degree. Then B, it will rotate through 30 degree. It will have a step of 30 degree. Then sequentially B and C together 45 degree. Then C alone 60 degree. Then A and C together 75 degree. Then A alone you will get 90 degree. Then A and B together you will get 105. So if you put A, B, C, A on this side, that is one phase mode, one phase on, and another is on the right hand side, it is two phase on. The combination of this, that is A, AB, B, BC, C, CA, A, AB, will give you a half stepping, that is the angle will reduce, stepping angle reduces. Further we can obtain the micro stepping or mini stepping also. It is similar to the half stepping, except that here also in micro stepping also, two windings are excited simultaneously, similar to the two phase on mode. But here in case of two phase on mode, current flowing through each winding is equal. However, in micro stepping, the current flowing through, say, A phase is kept constant, say 5 milliampere, and for the B phase, the current through the B phase go on increasing with a very small steps up to its maximum value. Then later on, keep the current in a B phase constant, that is say 5 milliampere, and go on decreasing the current flowing through the coil A at the same steps up to a zero value. You will get micro stepping, and in this way we can obtain the steps angle 1.8 degree also. Generally used stepping angles are 1.8 degree, 2.5 degree, 7.5 degree, 15 degree, etc. Now, what are the applications of variable reluctance taper motor? It is used for toys, tape recorders, advanced clocks, printing machines, robotics, XY plotters, in a position controls, in a process control also, in feedback controls also, and for positioning the objects, etc. So in this way, we have learned the general information about the taper motor, then the step angle, resolutions, then variable reluctance taper motor, why it is called variable reluctance, its construction, principle of operation, single phase mode operation, two phase mode operation, then half stepping, micro stepping, etc. and finally the applications. We'll stop here. Thank you very much.